Welcome everyone, my name is Barry Kersbergen, and today I'll present our work on the scalable data debugging for neighborhood-based recommendations with data-Shapley values. This work is motivated by the real challenges we face when running recommender systems in production. We'll show how the ideas of cooperative game theory can improve the reliability of recommendations, and this work is done with Olivier Sprangers, Brian Carlas, Maarten de Rijken, Sebastian Schelte. Real-world recommenders are trained on clicks and sales, billions of messy interactions. And this noise can come from malicious sellers or bots, or innocent cases like multi-journeys where people are buying gifts for other people. If left unchecked, the consequences can be quite serious. For example, Amazon recommending bomb ingredients suggested together, or recommending AI-generated books filled with nonsense. At Bol, an online Dutch retailer, we also had an incident where adult items were recommended to children toys due to data co-occurrences together with metadata issues in our catalog. So our goal is to filter these harmful noises and prevent, while preserving the valuable signals that make recommendations valuable. So in machine learning, there's this notion of data importance. If we remove one data point, does the model get better or worse? And that's the intuition. So formally giving a data set D and a utility function V that measures or evaluates the performance of S, which is a subset of D, we ask, what is the contribution of each data point in your training data? The simple method is to leave one out. We remove one point, retrain the model, then evaluate the change. We measure the change. It's very simple, but it's also unstable. A more principled approach is the data-Shapley value, inspired by cooperative game theory, and it averages the point contribution among many subsets. And the negative-Shapley values indicate harmful data. And later I'll show how this helps recommendations to detect unsafe clicks and sales. The challenge is the exact Shapley values are intraceable because they require evaluating all subsets of your training data. A popular approximation is the truncated Monte Carlo Shapley values, which samples random permutations instead of computing all subsets. But even then, it still requires the retraining and evaluation of many, many models. And for recommender systems with millions of interactions, this becomes prohibitively expensive. So we therefore need a scalable approach. We focus specifically on KNN-based recommenders. So they might seem simple, but evidence shows that they can really rival or even outperform complex neural network-based approaches, for example, in session-based recommendations, session-aware, next basket, or within basket recommendations. So our interest here is not to work on model innovation, but on data valuation. Which of the interactions in our training data help and which hurt? And existing efficient Shapley methods are tailored specifically for classification problems. So they assume additive metrics, which don't really fit the ranking-based recommendations we are working on. So our aim is to design a general and efficient Shapley algorithm specifically for KNN recommenders. Our contribution is KMC Shapley, a scalable way to compute the data-Shapley values for KNN models. It's a general approach for efficiently computing the data-Shapley values for the KNN models, and it's an adaptation of the TMC algorithm. And our name kind of reflects that, the K for KNN and MC for Monte Carlo, which is kind of a nod to the original TMC Shapley. We avoid retraining by indexing all the training data once, and then we scan the permutation of the nearest neighbors instead of the whole data set. And we can skip evaluations, utility evaluations when the neighbor set hasn't changed, because then we know that its marginal contribution will be 0. So together, these optimizations, together with some small optimizations, make KMC Shapley up to 3 orders of magnitude faster than the original TMC Shapley while producing the same results. So we tested the KMC Shapley on several data sets, including millions of clicks in these data sets to verify its usefulness. We did a removal experiment. So we removed the data points ranked on their Shapley importance. And the results were clear. If we remove the harmful points, the ones with negative Shapley values, the model improves. If we remove the helpful data points with positive Shapley values, the model performance becomes worse. We also added, by contrast, some simple baselines like random removal, leave one out, or simple heuristics, and these have little effect. So this shows that the data Shapley values really capture which points matter across public and proprietary datasets. Beyond quantitative evaluation, the negative Shapley values also help us diagnose which specific kinds of harmful sessions we have in our training data. For example, we found a session recommending a foldable laundry basket when a customer was searching for a baby bath, which is clearly a dangerous advice if a parent would take that seriously. Other negative sessions had poor metadata, for example, blurry product images, bad reviews, or important product attributes that were missing. And this caused the recommender to recommend irrelevant products, and surfacing these cases now lets us improve both the user safety, but also the recommendation quality. To conclude, data debugging is not a luxury, but a necessity for real-world recommender systems. So our contribution is a scalable method, KMC Shapley, that makes Shapley values practical at RecSys scale. It reliably identifies both beneficial and harmful data, enabling targeted data pruning. And this improves the quality and the safety of recommendations and even opens up new directions like ecological sustainability by pruning data linked to unsustainable products. All of our code is open source. You can just do a pip install. Thank you, and I look forward to your questions.
Thank you for a great talk. Can we assume that noisy data for KNN is also bad data for another models, like matrix factorization or any deep learning model or anything? I mean, if you can find the noisy data by this method for KNN, you can safely remove the data even for training another type of model.
If I understand correctly, I think you're asking the generalizability to maybe neural networks?
Yes.
So we tried that because if you see these noisy sessions and data, you would reason like maybe it also works. So we tried experiments on all state-of-the-art approaches for session-based recommendations. And there we see that it kind of generalizes well to neural networks as well. So that could be an interesting follow-up research direction to explore, maybe use this very cheap KNN neighbor to identify these noise and then have a separate approach to really make it work. It didn't fully generalize, but there are strong signals that, yes, there is potential there.
Isn't a limitation that you mentioned in, or maybe an open challenge that you mentioned in the paper, that we need to understand how to efficiently maintain the data importance scores incrementally as the new interaction. Can you elaborate more on that?
Yes. So academic data sets are like usually static, given you have a data set, but this is not how we observe data in industry, where everything is a sliding window. Oh, sorry. So tomorrow, today's data will be added, and we remove, maybe if we use 1 year of training data, the last day would be removed. So if you take 1 year of data, that will be like less than 1% of data change, but using this existing method, you would have to recompute estimate all the Shapley values again from scratch. So this is a very inefficient way of computing it. Even though it's scalable, it's still inefficient. So we think there's room for improvement. If you only change like a fraction of the data, how can we do that more efficiently? So that will be interesting follow-up work for people to work on. Please do and inform us.
Can Illuminate be used for no recommendation datasets too?
There seems to be potential, yes.